Minimum maximum principle number 2 is very similar to minimum maximum principle number 1, but instead we're going to use the second derivative in order to classify the particular point. And it only works when there's one critical value in the interval, unlike previously. So it's a little bit more specific. So let's just go ahead and read it. It says, suppose f is a function such that f prime exists for every value on the interval, aka it's differentiable. And there is exactly one critical value in the interval for which it is 0, not undefined. Then f of c is the absolute minimum maximum if its f double prime is less than 0, aka concave down, and fc is the absolute minimum value if the curve is concave up. So basically this is saying we have a some interval and there's exactly one critical value in this interval where it's got to be continuous and the derivative has to exist. Basically, if it's concave up, it's going to have the absolute maximum value at that particular interval. Again, assuming that it's concave up at that point. And if it's concave down, also, the fact that it has only one critical value is important, because let's say we were looking at an interval I that had more than one critical value in it. Like, that just means it has two different turns in the graph. Here, we don't know that a critical value associated to that, again, this part of the curve would be concave up. We're not really sure that this is the absolute min, and it doesn't really make sense. But if you're kind of restricting it to having just one critical value in the interval, that means it only has one turn. That point has to be associated with the absolute min on the interval, assuming it is concave up, again, as it says right here. Or in the opposite way, if there's only one turn, that means you're only allowed to have one critical value. The concavity will determine the behavior, and it will be absolute at that. So the first derivative of f we already did above, but that was 6x squared minus 6, which would mean the second derivative would have to be the derivative of 6x squared would be 12x by power rule, and the derivative of a constant is always 0. And so there we have it. And the idea behind the min-max principle is I can use the second derivative to classify the absolute min or max on the interval, assuming there's only one. So like in the prior example, there was only one critical value in the interval -3 to 0, which was the -1. And that basically you could use these principle 2 here or here because there was only one critical value between 0 and 3, 1. But you could not use the min-max principle 2 on this sort of interval because there's multiple critical values in between the endpoints. And also what's nice about this is you don't have to do all the math. You don't have to check all the endpoints. You just literally find the critical values, make sure there's only one. So in here, the only critical value was -1. And then I just plug that into the second derivative to determine the concavity. So I then check, well, what is f double prime of -1? Well, f double prime is 12 times x, so 12 times -1 would be -12. -12 is obviously less than 0, or negative, which again, that implies that is concave down. And remember, when it's concave down, that always means maximum. And because that's the only critical value on the interval, this has to be the absolute max on the interval -3 to 0. And this would be our final conclusion, that the absolute max occurs when c is equal to -1. And again, I know that point, we already found this point above by doing it the other way, but I could always solve the y value by plugging it into the original function. And notice this is consistent with what we got above. But the principle only identifies the behavior of the critical value and not the endpoint. So it's a little less work, but it doesn't figure out the rest of the endpoints, obviously, because we're not doing that math. And similarly, if we're looking at the interval 0, 3, the critical value there was at +1, and all I have to do is check the double derivative, or the second derivative, at +1. 12 times 1 is, of course, 12, which is concave up, which implies we have an absolute maximum. Concave up means it looks like this, which means there should be a minimum at the bottom of that type of shape. And it has to be absolute on the interval again, because it was the only critical value, at c is equal to 1 on the interval 0, 3. And again, I could find the value by plugging it in. As we did above, we found that that occurred, was at 1, 0. And it's the point 1, 0. And sometimes you could be asked to answer, what is the minimum value? The value is always the y value, the location is the x, and or sometimes you might just be asked for the entire coordinate of the point.